All right. Great. I'm glad to be here with you today. My name is Myrick. I'm supporting some wireless time development work with Nobu, Julian, and Ahmad. So I just wanted to present to you some of the results that we are exploring right now or getting with what we're calling the IoT software-defined radio. So we have some pretty cool results, and we're going to see where we can go from here once I provide the presentation to you today. So to give you some background about me, so I work for a company called Ensco, part of the advanced programs that's associated with the Mission Systems Group. What we do is we look at a lot of type of wireless time synchronization approaches. We look to deal with a lot of high precision ranging. We've developed ranging devices, and one of the things that's interesting about this project with Ahmad is to say, oh, is there anything we could leverage from some of the things we've done in the past that could support this project? And so we're looking to explore, I guess, seeing what kind of algorithms we've used to see how they can apply to the time card and impact the overall TAP community. So I want to give you a brief overview, at least, of where we start in terms of how we're supporting the TAP program. For the most part, there are two TAP work streams that we're sort of involved with. The first one is the time card project. That's how I got initially involved with the group. They provided me a time card to try to figure out, is there anything we could do with respect to wireless time synchronization? So I had a chance to get a chance to understand what was there in the time card, how to use the time card, what are the nuances and things like that. And then I was introduced to the wireless synchronization team, which is being led by Nobu and Julian. And so that's, of course, work in progress. But I was able to engage with them about what they're considering as far as different kind of protocols for wireless comms and as it relates to the time card. So this presentation is sort of a fusion of sort of the both, or at least exploring how one can leverage wireless synchronization with the time card and what are the protocols that one could use to actually do that. One of the things, you start talking about IoT and you say high precision, doesn't quite line up because there are a lot of constraints when you're talking about IoT devices. So this chart, this slide, I just want to talk to some of the things you have to deal with when you look at this particular type of research. One of the things, of course, is the Internet of Things implies low bandwidth and low power. And then when you say that, low bandwidth, low power, that usually doesn't imply precise time synchronization. And then on top of that, low power normally implies limited clock stability. Because as you noticed in this realm, right, when you talk about clocks, stability is the big thing in terms of what you want to have in terms of time transfer. So how do we work around those things? What are the things we're exploring in this research to try to figure out how to get around that? And that's part of what I'm looking at, is looking at the different kind of protocols in the IoT realm and determining what can we do to get around some of those constraints. And then also put it in the context of a software-defined radio. As soon as you say software-defined radio, now you're opening up the aperture in terms of different kind of protocols and different type of clocks that one can use. So I wanted to show this chart. It is an eye chart, but it's mainly for you to look at this presentation afterwards and just see all the varying types of IoT SDRs SDRs that are out there. There is an IoT SDR that actually exists that's on the web if you look at it from Crowd Supply, and they have the various specs. The biggest thing I want to say here is that when we talk about IoT SDRs with respect to time cards, it's really about the clock stability again. And I'm driving home that one arrow that I'm showing there is that green arrow. It shows the frequency stability. And all of these, they're part per million in terms of the frequency stability. One of the things that we considered when I was talking with the team is making sure that we actually have a very stable clock that's a little bit better than what you would normally see for a typical software-defined radio. And that's one of the things that was part of the design space in terms of what we wanted to create in terms of IoT software-defined radio. The other thing is we're going to be looking at measurements of time of departure, time of arrival. I'm going to show some initial results on that. And then that will reflect to how the frequency stability is being accounted for as well. So I wanted to at least give you an overview of the IoT SDR and the current prototype that's available, that's been developed. Julian, I don't know if Julian's in the room, but he was able to create a very nice card. This is really based on using an RCB header. So I'm going to show in the next slide why we did that. I wanted to be able to actually do plug and play, and as we come up with different kind of cards that are based on software-defined radios, we may want to change the different kind of protocols or transceivers that we're using within the card. But this just mainly shows an outline of what we're wanting to do and the type of setup in terms of the flow chart. The biggest thing here is sub-gigahertz for carrier frequency in terms of using that as a way to explore time transfer. And then also the low frequency antenna aspects of this. So if we can enable or allow signals like 60 kilohertz WWVB, then again, it's another alternate source of timing that you can provide to the time card. So both of those are pretty much fused in this one card, and we're seeking to figure out, with that fusion, what can we do in terms of providing the precision that we're needing to provide to the time card. And of course, one of the things we're interested in is the spectrum, right, of precision that's associated with timing. So from 1 millisecond down to picoseconds, what's the technology that allows you to play in that range, and then what's really feasible within this construct? So I wanted to do a quick overview, at least, of what we were able to see in terms of the design and why we chose the RCB header design. We could have chose other ones. I wanted to use the flexibility of the time card. Time card is very interesting, right? There's a time card instantiation that has 2 GNSS receivers. One idea is, well, maybe I want to replace that one GNSS receiver with this IoT SDR. Well, what does that allow? Well, that allows me to have other ways of bringing in timing signals within that time card. So the idea is I have a diversity of signals that I can use to support the time card, as well as potentially provide a way for time cards to communicate with each other. So I may want to have time transfer between time cards. Assuming one may not necessarily have the best signal that's available, I can then use wireless time transfer and the potential Wi-Fi protocol in order to actually achieve that. So that's one of the reasons why we wanted to highlight using, or at least creating, the IoT SDR based on this RCB header. So one of the things I want to talk about is give you a quick overview, at least, of a snapshot of how we're processing the LoRa signal. I don't have a lot of time to get into the details of this. You can always talk to me afterwards, but at least I want to give you an overview of what we're trying to do here. In terms of time transfer, first of all, Wi-Fi is based on the two-way time transfer technique. And it's able to cancel propagation delay, right, associated with the channel. And with that, you can get high precision measurements. One of the key things is, well, how do you do that when you talk about other signals, narrowbandwidth signals, especially when you're talking about IoT? It's a characterization of how you're figuring out, first of all, with two-way time transfer, there's one measurement is one way, another measurement is another, time of departure, what we're calling it, time of arrival. Taking those measurements and being able to cancel out the errors. But in addition to that, what's the right way to synchronize and extract that timing information from the signal? This is just a quick overview, at least, of 2 snapshots that were taken with the IoT SDR. One is from what I'm calling the primary, and the other one is called the secondary. And those are the symbols or the chirp spread spectrum signals that were being generated from the LoRa transceiver. And I just want to give you an overview of what we're sort of looking at. This pretty much spans milliseconds, so it's about 10 milliseconds span, and it's about 9 symbols. But that is the framework of the data that I'm going to use to show you the remaining results. Now, before doing that, I want to give you a quick overview, at least, of some of the things I've done. In 2018, I did some work with GNU Radio, and I was looking at RTL SDRs. And if you're not familiar with that, that's another inexpensive SDR that allows you to do capture of sub-gigahertz type of wireless protocols. Here, I wanted to show, or at least indicate, that typically for a LoRa packet, you have what they call the preamble, and then you have the symbols that come out the preamble, which are pretty much scrambled. One of the key things here is I wanted to do in terms of this research was to figure out, well, can I create a way to do synchronization or time transfer with both the preamble and with things that are being scrambled as well as part of the data? And this just shows an example. If you're going to look at Wi-Fi from a one-way perspective in terms of the transfer, this is what you would receive typically, where you have a higher power signal at the primary, then you have a lower power signal at the secondary. But ideally, you're capturing the same information, and then I can do cross-correlation to figure out the time difference of arrival. Next, the opposite occurs between the secondary and the primary. So then at that point, I'm also transferring information back. You can notice here that the capture is a little bit stronger, have the receive that's going to be weaker. And then with that, I can now get time difference of arrival going the other way. And the combination of time difference of arrival for both secondary and primary are combined such that I can figure out my actual propagation delay as well as clock offsets. Okay, so quick overview of the architecture. Basically, with time of departure being measured and time of arrival, what we did, and I didn't say this earlier, is that one of the things about this IoT SDR is a hybrid architecture. When I say hybrid, it means I'm using existing transceivers to help generate some of the waveforms. Rather than just depending on the FPGA to generate the waveforms, I want to use the existing transceivers. Why is it important? Well, for prototyping, it allows you to quickly get something up and going. And it also to leverage whatever nuances or things that are important within that transceiver that you may be able to leverage to help with the synchronization. So I thought that was very important as well. But this is pretty much the setup that we had in terms of the data capture, how we stream the data. One of the key things is here is that we're sampling a little bit more than what's necessary. We had a 250 kilohertz bandwidth of a LoRa signal. We oversampled by 4. That's important because you see later on when it comes to sampling and figuring out the time of arrival, time of departure, it comes into play. So one of the things we did was we used one of the techniques. This is another paper I did a couple of years ago where I figured out a way to do what I call co-bit adaptive processing. What it says is that if you can take a waveform, is there a way to break up the waveform such that I can look at it in terms of slow time and fast time? And I'll give you a quick overview of what I mean by that. Fast time is pretty much the way I break it up in terms of the symbols or packets. And then slow time, well, let me reverse that. Slow time is usually when I consider the number of symbols and packets that I'm using. Fast time is usually in the domain in which I'm actually doing the chirps. So you can look at it from a code bit domain in which the coding is associated with the chirps and the bit domain associated with the symbols. And you can figure out a way to then do signal extraction when it comes to phase and to frequency. So I can't get into too much about how I did that, but I just want to give you an overview of that was the sort of process and the algorithm that I used in order to generate the results. Quickly, I want to show you some results from this in terms of the work, and then at that point, I can try to take some questions. For time of difference arrival, the big thing is TOA. How do you get precision or accuracies that are a little bit better than what your sampling rate is? Well, you want to oversample first, and then when you oversample, that allows you to do linear interpolation or sample interpolation between actual samples. So here I was sampling at 1 megasamples per second. You can see, at least from a packet, if I did not use sample interpolation, I was either 0 or was off by like 1 microsecond. But then when I added my sample interpolation, now I'm able to get, I was able to resolve better than 1 microsecond. So then now that gives me an additional refinement associated with the packets. Now, let's keep track of what I'm doing here. Packets are just the whole set of information I'm sending every time I want to do a transmission for my TOA. Now, that is what I'm considering sort of the slow time. When I go into the symbol space, that means I'm looking at the symbols per packet, and I'm doing TOA in that. So now for every 9 symbols I have per packet, I have 9 additional measurements that I'm applying the time of arrival to. And this is what you see here in this result, where, again, it matches the other, but now I have a fuzz that's around the original packet number because now I have 9 symbols that I'm extracting that time information from. Now, that was for time of departure. Time of arrival now is on the other side, where I've actually gone across in terms of transmitting from one software-defined radio to the next. In this case, I wanted to emphasize and show the TOAs associated with that. I zoomed in real quick just to let you know you're getting 20 nanoseconds in terms of the actual error itself. All right, since I've run out of time, I wanted to just do a quick summary. You can actually do clock drift as well. That's associated with that, and that's measuring the phase. And I was able to measure the phase after finding the TOA associated with the signal. And to summarize, our plan is to continue to make these measurements, do measurements with the LoRa protocol and continue to see how we can develop this and determine range and other type of wireless IoT signals that are available to you. And you can talk to me after this talk if you have any kind of questions about this. And that's pretty much it. Thank you.